But we're talking with a few people that are in class today, and hopefully I'll be able to get this posted after we're done. We have a couple of things we want to do. One, of course, is to talk about the final. Exam 2 is kind of in the background right now. I will talk about that in a bit. But we'll talk about Appendix A. And I don't know, those of you that are in class, did you watch the video that I made the afternoon before I left? I just made a short video to compress the last bit of Chapter 4 and part of Appendix A and Project 2. I did all of that stuff just before I left. So there is a video up there. So we are going to start in Appendix A. We're not going to finish anything off in Chapter 4 unless you want to talk about it, because I did put it in the video. I can refer to a few things, though, as they pertain to studying for the final exam, of course. But let's get into Appendix A and then see what's going on there. The good news is that Appendix A is very straightforward analysis and calculations. No real Python calculations. We could be using LT-SPICE. It's more or less circuit analysis and looking at physics of noise in electronic circuits. But then it takes that all the way forward into systems level modeling, which is the type of stuff I've definitely done in my work at Emergent, which is now Khaki Systems, Emergent, whatever. But I've done things with all of this stuff towards the tail end. So I briefly went through the physical noise source modeling aspects when I recorded my video just before leaving town, but I will hit some highlights of this. And then I said that I would be covering sort of the systems level modeling of noise in receiver circuits, which is part A2. And then the last part is a free space propagation example, which is Appendix A.3. What did we miss from Chapter 4 that I'm just going to go back and talk about very, very briefly? Besides what we left off with the last day, I guess maybe I drew on this when I was writing, so I can't say. I don't remember. Did we go through this in class, quadrature multiplexing? I can't remember back that far, because all I know is I talked about it during the lecture I made the week before I left. This is also a fundamental concept, but it's actually the concept that's used in digital modulation all the time, where you have in-phase and quadrature. It could be analog in-phase and quadrature. In the case of Project 2, it's digital waveforms on the in-phase and quadrature, and they travel over the channel, maintaining their perfect phase quadrature, because if you go ahead and demodulate with a cosine carrier or a coherent sine carrier, you get back, assuming the phase difference, phase error in the demodulated carrier is 0, you get back exactly M1 and M2 on 2 different channels. And normally they're referred to as the in-phase and quadrature channels, so they'd be made up into a complex waveform at the receiver, but they could be separate analog channels. If you were doing it in purely analog, it would just be two waveforms. So I'll get back into this when I go through the review, but this is a fundamental concept, the so-called quadrature multiplexing. And multiplexing is kind of the theme that was introduced just prior to this. And I'm going to spend more time probably looking at this again too, because this shows up, I think, in the old exam. I think I have a question in one of the old exam 2s, but I'm pretty sure now that I'm looking at this, I talked through this example of multiplexing on the video I made just before I left. So backing up further, I guess I'll just get into the whole thing. Frequency division multiplexing is where you decide that you want to combine multiple signals and send them through a common carrier. We talked about in chapter 3 at the very end time division multiplexing, and I know I put on exam 2 an example of time division multiplexing, right? And that is something that without communications theory you'd say, oh, this is digital logic, right? I'm going to just take some logic waveforms and multiplex them together. The other side of that is to do frequency division multiplexing, and this is age old, the concept. It's been used in the first generation cellular, and it's being used in all sorts of things to this day. And it has somewhat different forms, but the basic idea is you're going to locate signals on different subcarriers. In the case of first generation cellular, it wasn't subcarriers per se, it was just that we had what was called frequency division multiple access, where everybody could access a different frequency slot and be separate from other users. And then when we evolved that into generation 2, we had frequency division multiple access with time division multiple access. In other words, everybody gets a channel, but they have to share it with many other people, 6 other peoples on one of the standards that came around and we've gone through. But then everybody gets a slot, a time slot in addition to a frequency slot. So hopefully, being that we've been through the whole semester of communications theory, you can recognize that we can slice up a channel in different ways. Time division, Muxet, frequency division, and then we can do combinations of the two. But this scheme is used in SATCOM today. It's used in broadcasting, and it's actually used in other forms, even in fiber optics. It could be used in a single mode fiber where you would modulate onto the fiber many different channels of information. And this shows it as analog. It can be digital, but the idea is you're going to put subcarriers. So you're going to put message 1 on a subcarrier FSC1, and then you're going to put message 2 on FSC2, and as many of them as you want to combine. And then you're going to take that composite baseband waveform and put it into an RF modulator that's going to put it onto the carrier frequency. So I'm really tired right now, so I'm not maybe going to say, oh, this is crystal clear. To me, it's crystal clear, but does it make sense that we can have sort of a carrier at a really high frequency, and then at baseband we can combine a bunch of signals at different subcarriers and put that composite up on a carrier? And I'm going to show an example of this in the old exam, actually. I'll get right into that because that was something that was on, remember there were 2 old exams for exam 2, and there were problems on there that were beyond where we were in class, but are definitely candidates for the final. So I'm going to segue right into that little workup following this. But at any rate, this could be, the RF modulator could be an AM modulator, it could be PM, FM, it can be any type of modulator that you want it to be. The main idea, though, by putting in the subcarriers is you're going to give each subcarrier a different slot in the subcarrier band. So I'll try to draw a simple picture. That might be F, and you're going to you're maybe going to have one subcarrier at 0, then you'll have another subcarrier that has the upper and lower sideband, or I mean, it's a real signal modulated by another subcarrier. So this would be FSC2, let's say, and maybe FSC1 equals 0, and then you could put another one and another one, and as many as you want. The main thing about FDM is that all of these signals have to be disjoint. In other words, they don't overlap. Does this make sense? I can just put them up there in the frequency domain, And then I take this composite spectrum of all these FDM'd subcarriers, and I don't know why that went off. The screen did not change. At any rate, modulate those on a carrier that's going to transport all of them through space, and then you receive it, and you first demodulate it off of the subcarrier, and then you demodulate the subcarriers. So I've already said it, at the receiver, we demodulate the composite signal, and then demodulate the individual subcarriers. So the way this has to work most intelligently is that you will demodulate the composite baseband signal off the carrier, and then you will have bandpass filters to make sure that any noise, any other interference that might just overload the front end of the individual subcarrier demods. They're not going to be at the frequency of this subcarrier, but they're still going to be close enough that they might cause some problems, so you just isolate them with bandpass filters. Does that make sense? Just isolate another bandpass filter, and then you demodulate the subcarriers. So the telephone company recognized this early on, where they were going to do single sideband subcarriers, and that way they could pack as many subcarriers together as possible. Because remember, what's an advantage, if I ask this question on the final, what's an advantage of single sideband over double sideband in terms of spectral efficiency? Half the bandwidth, right? So that's what they did ages ago. And like I've already said, it could be analog, digital, it can be a combination of the two. There's all types of variations that are out there. So a classical example that I did go through in this lecture, that's why it got marked on, that I made before I left, is FM stereo broadcasting. How did we get FM stereo? Well, Armstrong, remember from the first day of class, was the inventor of FM modulation. And he came up with this back around 1900, 1910, or whatever it was. And then it became a broadcasting standard. I don't know if you remember this story about Armstrong. AM radio came on the scene first. Armstrong came up with the super heterodyne principle, which is the frequency translation and mixing, all the stuff that we've been through in the class. And those of you in the lab use this a lot, right? You got really good at it and understand how it works. He also came up with the FM, and the big companies on the East Coast were going to do AM radio, and they didn't want to have his FM radio idea take hold, so they kind of defamed him and took him down, basically. He died, a poor man without any money, I think, and his FM idea eventually took off. And in the 40s, they started proposing that, hey, we could do stereophonic broadcasting. And that was an amazing feat, that you could have two channels of analog material sent over the same carrier. So that's a good example of frequency division multiplexing. In the case of FM stereo, at baseband, you send one message, and that message is left plus right, which is formed in this matrix operation here. You also send a pilot carrier at 19 kilohertz, and then you double sideband modulate on a 38 kilohertz subcarrier, the difference, left minus right. All three of these combine, and then they go into an FM modulator, and in fact, they go into the standard FM broadcast modulator model of 75 kilohertz peak deviation, and so on. And now what you're doing is, when you're broadcasting, your baseband signal occupies more than just, say, 15 kilohertz. It goes all the way up to 53 kilohertz. So why do you suppose, what's the point in having the 19 kilohertz pilot? Before I go to the next part of the page. What's one disadvantage of double sideband or coherent modulation? You have to have a coherent carrier at the receiver, right? Phase lock loop or some recovery means. But that doesn't preclude you from being creative, and this was back in the 40s, like I said, when they were playing around with adding this or augmenting the FM broadcasting standard with stereo. So they send a 19 kilohertz carrier, they frequency double that to be the subcarrier for the left minus right. In that way, at the receiver, you can come along at the receiver, have your FM discriminator, which gets back what? And if I give pictures of this on the final and I show something like this, or we'll look at a sample problem from the old exam too, that FM discriminator is going to get back the composite. It's just going to pull that composite right back here as X sub B for baseband. It's going to get all of these components back. And to get the left plus right, you just bandpass or low pass filter that at approximately the bandwidth of that part of the message. And then you take and use a phase lock loop or a narrow bandpass filter centered at 19 kilohertz. And then you double that frequency to 38, and that's phase coherent with the left minus right double sideband signal, and you can demodulate that. Again, a low-pass filter. This is just the standard coherent demodulator for double sideband that we saw a long time ago. Just put it to work again. And then you go through the matrix operation here. I call it a matrix because it's kind of like 2 in and 2 out, but it's doing a transformation. Does that make sense? Is that fair for me to call it a matrix? So I get left and right. And in the olden days, before we had streaming media and the internet and everything else like that, there were other subcarriers put even higher in frequency, like 76 kilohertz and so on, for other purposes. Other telemetry data can be sent between, say, the studio down here in Colorado Springs and the transmitter up on Cheyenne Mountain. They can actually, in the olden days, and I think they still do this, they will put a subcarrier up at the transmitter, and that will be received with a receiver that can demodulate that subcarrier, and it might contain, housekeeping data on the state of the transmitter, which is some distance away. They also use this for background music. What is background music? When I say that, does that mean anything to anybody? It's a term that was used a long time ago, but we all experience it, but you probably call it something else. You ride in an elevator, it may be elevator music. It was a way of a broadcaster could put a channel up on a subcarrier and say, we're going to provide you with rock music or jazz or whatever, and you're going to get it from us because we're going to send it to you. Or it might be used in a doctor's office, whatever. That was before we had streaming media sources, Spotify and all that other kind of stuff that most offices or a gym will use that for their music. But this was something that was part of this standard. We already talked about quadrature multiplexing. So let's just go look at how this might appear and what sort of understanding I'm expecting you to have on the final. So I'm going to go over to here. And where I'm dropping into right now is I'm looking at this exam, spring 2019. Before I look at that, though, we'll just look at what set number 10, the only homework that's out there that hasn't been turned in. It's got a phase lock loops problem, and then it's got a multiplexing problem on it. And how are you going to work this problem? I'm going to show you what I consider to be acceptable. The book has solution examples in it too. I think there's at least one example in the book, but this is a very generic FDM system, frequency division multiplexing system. I'm just saying there's a baseband signal that occupies 25 kilohertz. There's a pilot at 30 kilohertz, and then there's a narrowband FM subcarrier at 40 kilohertz and a double sideband subcarrier at 70 kilohertz. So I ask you to draw the block diagram of the complete receiving system to get back the messages that are contained on each of the subcarriers. And when I say messages, understand it could be digital or analog and use coherent demodulation as appropriate and take advantage of the pilot. So has anybody worked this problem yet or thought about it?
I'm going to practice it once.
Okay, so I'm just going to give you some hint right now. If we have a pilot at 30 kilohertz, we're going to need to have, which of these subcarriers requires a coherent demodulator? Absolutely has to have one.
Duals or double pools, I mean.
Just the DSP, right? The FM can be recovered with a discriminator or phase lock loop, perhaps. The baseband is just right there. Just get it from low pass filter. So we have a pilot at 30 kilohertz. We're going to need to have a 70 kilohertz subcarrier. So you just need to put in your block diagram how you're going to do that, and you can be a high-level block diagram that just says, I'm going to do what? You're going to maybe multiply 30 by something and divide it by some frequency. Remember the synthesizer ideas. You might divide it by some number and then multiply it by another number. That's another way of doing it. So I'll let you bounce that around in your head, but I'm now going to go look at an example. This is an example from Exam 2, Spring 2019, and it's representative of the type of thing that could be on the final in this area. So here I'm just saying, here's the layout of the FDM system. It's going to put it up at 12 gigahertz. So I'm just pretending this is a radio relay link at 12 gigahertz. It's going to FM modulate the carrier at 12 gigahertz. Peak deviation of 1 megahertz. So what's the bandwidth required of that signal? So this gets back into Carson's rule, right? Remember where we would take the bandwidth of the signal. In this case, we'd say, what's the composite bandwidth? It's about 150 kilohertz, right? To take all those signals in the baseband together. And then the peak deviation is 1 megahertz. So we can use the deviation ratio is just going to be delta F, 1 megahertz divided by W, which is 150 kilohertz. So the bandwidth of that signal is going to be, if you just work through Carson's rule here, 2.3 megahertz. So it's really tiny compared to 12 gigahertz, but it's just an exercise to just carry that through. That's an approximation, obviously, but it gives you a general idea. Then when you want to draw out the block diagram of the receiver, this is the type of thing that I would expect to see. You're going to probably pre-filter the 12 gigahertz signal with a bandpass filter. You know that its bandwidth needs to be only 2.3 megahertz. You're probably going to end up building a filter wider than that just because it will be really expensive to make such a narrow band filter at 12 gigahertz. But that doesn't mean you can't draw the block diagram of the concept. So there's only a few of you here, but what's the idea about communication systems when it's all said and done at the end of the semester now? You learned the detailed modeling and then you have high-level block diagram modeling, and that's just something that should be a major takeaway from this class. If you took control systems, you learned similar types of things in controls, right? So these high-level block diagrams are kind of the starting point for most everything that a communications engineer ends up doing. The guy I work for at Emergent, we talk about this, that, and the other thing. We're developing algorithms to prototype in Python, and maybe it's in C++ or something, but he'll always say, do we have a block diagram of this yet? Because he wants to be able to take what we have to accomplish and be able to cast it into a block diagram that then can be presented to the customer and say, these are the things we have to do to build this system for you. So this is a excellent place to get started. So we have FM demodulator. Details don't have to be in there. It's just something that's going to demodulate FM. How you implement it would be another level of detail. If you wanted me to explain how I could ask more questions on this problem, but I doubt that I will because we have a lot of material to cover on the final, I could say, give me 2 ideas about how you'd FM demodulate. And to me, tops on your list would be just a traditional discriminator, an analog type discriminator, or maybe a DSP-based discriminator, or it could be a phase lock loop. Those are the two types we talked about in class, right? Both can work, differing amounts of complexity. Now we have the composite baseband signal, so this should be the composite signal, MC, so it's going to have all those components in there. We just want to recover the individual messages, so just like what I had in the notes, a low-pass filter to get back the M0 signal. We're going to get back the FM signal that was at 100 kilohertz with another FM demodulator, but we're going to precede that with a bandpass filter. And those are the basic requirements. So whenever you have a block diagram like this, you have two pieces of information. You should at least provide the center frequency of a bandpass filter and the bandwidth. If it's a low-pass filter, it's the cutoff frequency. So at any rate, that's dealt with here. FM demodulator. We would set the cutoff frequency of the low-pass filter probably at the bandwidth, which would be the bandwidth of the FM message, which was described, I think indirectly was described here. It doesn't really say. All you know is that the deviation ratio is 19. So from that, you can come up with an approximation, but that's probably not the most important thing in the problem. But it's around 20, I guess. 2 times 20, so it'd be 40 divided into 100 kilohertz. Okay, the narrowband bandpass filter or phase lock loop to take that the pilot carrier at 15 kilohertz. In this case, I chose to show it as a doubling to 30 kilohertz so I can coherently demodulate the double sideband and then pull it back to 10 kilohertz. And you know that the bandwidth of the message over here must be 10 kilohertz because the bandwidth of a double sideband signal is 2 times W, right? So it's 20 wide divided by 2 is 10. Does all this make sense? It's actually really easy stuff to do. And if I was you, I would say, great, I'm at the end of the semester. I don't want to work super hard. I just want to sort of seal off what I've learned, and I've got some good concepts, and I can, do this high-level modeling stuff. Any questions on it? I sort of covered one area of the final review just now. And it also is letting you know that there are sample problems on those old exams that will be useful. So back over to where we were. The very last thing that I put into Chapter 4 notes is this general performance of modulation systems and noise. And this gets really deep if you get up into the chapters that we didn't cover in Comm Systems 1, but just at a high level, back of the envelope type calculation, Dr. Ziemer provides a really nice analysis. He says, okay, a received signal is going to usually be accompanied by some receiver noise, and we're going to have to contend with that noise. So in simple terms, how does this receiver work when there's noise present in addition to the signal? So we're going to have some measure after our bandpass filter or something to just eliminate adjacent channel signals and so on. We'll have noise getting through this filter, subject to Appendix A actually, and we'll have signal power, PT, that'll be the total received power from the transmitter at the receiver, and that forms a ratio. So PT over this average of n squared, this is pre-detection signal to noise ratio is what it's called. How much signal to noise ratio do we have on our received signal before we demodulate it? So that's the lower axis here. And this curve then is called the general modulation performance in noise for a few different types of modulation that have been covered in Chapter 3 and Chapter 4. Digital modulation gets dealt with usually in a slightly different fashion, but we can still look at it in terms of the output signal to noise ratio, but instead we'd look at it usually in terms of the bit error probability, which is what you're doing in Project 2. So here we can just see that general response of double sideband, single sideband, quadrature, double sideband, all with a coherent demodulator, not an envelope detector, the higher performing double sideband with a coherent demodulator. It just linearly increases with the pre-detection SNR. The output SNR just goes up linearly. And this I've talked about times in the past. If you're listening to an AM radio station, you're driving, say, to Kansas, listening to a sports station on AM radio, it just gets noisier and noisier. It just sort of fades away gradually because you're starting here when you're in Denver, let's say, and you're going to drop down, and it's just going to fade into the background and get noisy or staticky or whatever. FM modulation, when we demodulate it with either a phase lock loop or a discriminator, we have an increased post-detection SNR. And why do we get this post-detection SNR? It's described in more detail in the advanced chapters, but I'm just telling you this deviation ratio D makes our signal occupy more bandwidth, right? Carson's rule. So we get a payback. We get an increased detected SNR out of that. D equals 10 gets us up to a higher post-detection SNR as the input pre-detection SNR changes. But we have this bad behavior in here. We have what's called thresholding. So the nonlinear modulation schemes, which is FM and PM, have a thresholding phenomena when noise is present. They just don't want to operate at high noise levels. But once you get above the threshold, you get a nice clear signal. And I think everybody has listened to FM radio enough to know that that's the nature of it, right? Strong enough signal, it sounds great. You start to get fading in it, and then pretty soon it goes away. That's the knee of this curve. So these are just different deviation ratios for FM. PCM, which was studied in Project 1 and then carried on into Project 2, is a digital scheme, but it's basically serializing the bits into words of so many bits per sample. And this plateau that we have, which you verified in Project 1, is just the signal to quantization noise ratio present in, say, the PCM scheme. More bits per sample, better quality. But digital communications has the same thresholding phenomena that FM does. It just happens at a different point. So this is 64 or 256 number of bits per sample. Actually, this is 2 to the n bits per sample. So this would be 8 bits, and this would be 2 to the 8th, and 2 to the is 256, and then 2 to the 4. Is that right? 2 to the 6 is 64. So this is just showing you how it goes up, and I haven't looked at very many papers as they were coming in, but everybody got something like this, right? Because I referred you to Chapter 8 to just see that it goes through a threshold, then it flattens. So this is just a general characterization, but I think it's useful to understand that, have a general head knowledge of what are general noise performance of digital modulation. So that was Chapter 4. If you want to hear more talking on it, watch the add-on video that I created before I left. So now we're going to go into physical noise sources, and I'm going to try to make this go pretty fast. It's not very difficult. It's actually pretty, it's a lot of fun, actually, because it's not very hard. The only thing that'll be challenging is, do you want to work with ratios or do you want to work with decibels? So that's how you can go wrong on an exam question, and I'm going to try to illustrate that. So the first part is physical noise sources, then the systems level modeling, and then the last part is just putting it into practice, like for a SATCOM channel, free space propagation, where we have antenna gains, gain over isotropic, and things of that sort. So physical noise sources, all electronic devices have internal, well, comm systems deal with both internal and external noise sources. The internal noise sources are just due to the physics of the devices themselves. It occurs in active circuits and in passive circuits. You can't avoid it. Why do you suppose that is? Some of you are really good at physical electronics. You have electron agitation, right? We're not operating at absolute zero, so we have random agitation of charge carriers and so on, producing noise. The systems modeling is, again, what I want to focus on, but we'll get at the origins briefly. Then the external sources that come along, in addition to the electronic circuits themselves, might be atmospheric, solar, cosmic noise, could be intentional or unintentional jamming. And those can be modeled as noise in many cases too. So modeling with external noise is very important. I mean, every radio system I've worked on always has a link budget, and SATCOM in particular. They want to know how much power they have to put on the out from the transmitter in space when it's running on a solar battery pack to get a signal down to Earth. So thermal noise is Nyquist's theorem. It just says noise due to random motion of charged carriers, and the basic equation is 4kTRB, where K is Boltzmann's constant, T is temperature in Kelvin, R resistance in ohms, B measured bandwidth. So this takes you back to physics and probably electronic devices that you've already seen in a previous class. But the basic system level model that comm systems engineers take is they say if we have a resistor in the circuit, it's going to have this either noise voltage source associated with it in an ideal noiseless resistor, or it's going to have a current source shunted against some conductance G. So these are the fundamental models. So if you had a 3 resistor circuit like this, what is the noise voltage produced at the output? Each one of these resistors produces a noise voltage, and you can assume that the noise voltages are independent so that you can sum the squares of the noise voltages and then take the square root, would be one way of doing it. Obviously, if your brain's thinking clear enough, even though it's in the early in the morning, why don't I just combine all those resistors into an equivalent resistance and I'll get it that way. That way works also. So we could do it using superposition, or you can use Nyquist's formula, which is kind of like the next step beyond Nyquist's theorem, which sits right here. When we have a resistor involved, we just assume a bandwidth that we're making the observation, and kind of like you have with the spectrum analyzer when you set the resolution bandwidth. I don't know if you observed those were in the lab. As you change the resolution bandwidth, the noise floor went up and down, right? It's because we're basically adding in a band limiting operation when we zoom in, and so we see less noise present at the receiver input because we're effectively changing B. At any rate, what is Nyquist's formula? It just says any RLC network, and now we're talking passive, will abide by this formula. It just says we look at the impedance looking into the terminals, and the noise voltage is going to be 2kT times the integral of the real part of the impedance of the network. Now this seems complicated because it has an integral involved with it, but you can just see that if we had a pure resistance in here, just an equivalent resistance, no other reactive elements, and then we took advantage of symmetry for this simple integration, we'd be integrating over some observation bandwidth minus b to b, so this 2 would get another 2 alongside of it, and this is exactly Nyquist's theorem. It's back again. The 4 KT RB is sitting in there. So we could just find the equivalent resistance there. Something that is not in the book, but something that I've been involved with years ago and different projects I worked on was to actually model noise in a circuit, and SPICE-like circuit simulators like PSpice. At one time, I used this piece of software called Quux, which the name of it is very bizarre, but it was really Qt, but Qt is a windowing environment, and the owners of the Qt software said you can't call your circuit simulator Qt circuit simulator. Sounds like a legal thing, right? So the authors of it, and I'm just telling you this because it's cute and you'll run into things like this over your lifetime. So they renamed it QUCS, and UCS is quite useful circuit simulator or something like that. They just made up a name. So when you use a circuit simulator, SPICE-like simulator, it will allow you to look at node voltages and branch currents just like you do with any AC circuit analysis. Now you're just in AC noise analysis mode when you're doing that in your SPICE simulator. And it's going to give you the RMS noise voltage per square root of hertz, because it's assuming that you're going to get the noise power, but you're going to take the square root. So you're going to be left with bandwidth, which normally is sitting on the right side, but you're now going to have the square root of bandwidth on the left side, and you'll have it as a function of frequency then. So in this circuit, this was the circuit that I had in the notes. I just had the same 3 resistors in here. I guess 4 resistors, whatever I had. This was the circuit I analyzed. I said, just do the simulation. These are all the resistors, equivalent resistance. R equivalent is 25.93K. If I plug that into Nyquist's formula, I can just put in that equivalent resistance, and then I can remove the bandwidth and just assume it's normalized by the bandwidth, the square root of it. So 2.072 times 10 to the minus 8 volts RMS per square root of hertz bandwidth. And the default in SPICE is generally 300 degrees Kelvin, but that's one of those parameters you generally don't mess with. Has anybody ever done SPICE, LT SPICE, where you change temperature? What class did you do that in? I'm just curious.
I think it was for my independent study.
Okay. Okay. But I think at 300 or 290 is the default. I've had to change it too. So here's what it gives me in the plot window. It's just going to give me flat versus frequency. This value, 2.072 times 10 to the minus 8. If you put a reactive element in, like a capacitor, let's say, now you're going to be able to have some real part of the impedance be a function of frequency, and then if you sweep it out, you'll just see that it's going to change. There's going to be more noise at some frequencies than the other. But just to prove that the theory makes sense, if you take this circuit right here, at really low frequencies, the capacitor is going to look like what? An open circuit, right? There's no capacitive reactance. It's very tiny. So it just looks like 3 resistors. And at very high frequencies, this looks like a short circuit because the reactance becomes really small. And that's exactly what's going on here. This is like the open circuit, and this is the short circuit capacitor. So these are the two noise voltages, and I wrote out the impedance using circuit theory and just wanted to verify that. And again, you get this guy as a function of frequency now because the impedance is a function of frequency. Why am I going off on this tangent? And I probably should pull back to get on other things that are relevant, but I'm just kind of entertaining you with things that you may bump into. I worked on a project once for a GPS company that's still in existence called Navsys, and we were working on a frequency synthesizer, and I had problems with the op amp that was used for the loop filter in the synthesizer ASIC, and I got into looking at the op amp. So I studied the op amp in active circuit, and I said, it's now got noise due to the electronic, the active circuits. So I looked up the op amp noise model, and it's got two current sources in shunt at the input, and then it's got a series equivalent voltage En. And then I went to the data sheet, and I did this for the old 741 op amp, the really antique op amp that's still used. You guys learned about it, I think, too, right? Didn't you bump into it? 741. It's kind of like the standard that was the very first op amp that existed. But you can put those parameters into LT Spice, and I put it together in Quux, but LT Spice would have been similarly. I set attributes of the op amp, and the op amp has a dominant pole compensation in it, so it rolls things off, but this is what the noise looks like. What I ended up doing in this project was I replaced the low-cost op amp with a low-noise op amp to try to reduce the amount of noise coming out of the op amp that was introducing phase jitter or phase noise in the synthesized output. That was a nice thing to do because I was suspicious that that was the problem. But in the very end, I'm just telling you what I ran into, and this is a typical engineering scenario. You go chasing after things that you're looking at saying, I bet this could be a factor. So I redesigned it, found a low noise op amp was a good choice for a low phase noise synthesizer. But it turns out one of the capacitors that was used in the loop filter design itself, this was a analog loop filter, had been treated with a chemical to clean the solder flux on the PCB, and that solder flux cleaner got inside the chip capacitor and messed it up. So now it became a very noisy electronic component. How did we figure that out? Took the capacitor off and put it back, a new one back on the board, did not clean the board, and the problem went away. So I remember one time when I was teaching capstone design, I had somebody come in to give a guest lecture in that class, and his story was all about some electronic device that had been messed up by bad chip capacitors. Not for the same reason, but they were bought from a vendor in China or somewhere. They were just all flawed, and the customers were all having issues with the device, and it had to do with the chip capacitor. Something you take for granted ended up being the problem. Okay, other types of noise in electronic devices is shot noise, which is related to average current flow, and special case PN junction, and you get into modeling the device physics, and that's where I was thinking some of you maybe bumped into this in your device physics class. I worked with optical communication, so I had laser diodes, and then PIN diodes were used, or not pin diodes, but what type? I'm trying to remember what type of diode I used for the photodetector. So I was dealing with shot noise at that point. So these are just some of the other things that can contribute noise to receiver electronics. Generally, as a systems engineer, you're not going to be at this level. So now we get ready to transition into the second part of this appendix. The systems level model wants to just think of the receiver front end as a signal that's coming from an antenna feed line, and then it goes into your receiver. So what are the types of things we'll be dealing with? We're going to be dealing with components that are interconnected with RF transmission lines, and the transmission line impedance is generally going to be 50 ohms. But in cable TV systems, it's 75 ohms. But the idea still is that we're going to transfer a signal from point A to point B, and we're going to use a transmission line. And the idea with the transmission line to transfer the information is to match the impedance from the source end to the load end to not have reflections or standing waves on the line. So we're talking about maximum power transfer when we do that. Maximum power transfer for a voltage source just says the load should match the source resistance, or if it's a current source, the conductance of the load should match the conductance of the source. So you can go through this sort of modeling. So the power delivered to the load is related, is the available power when we do conjugate matching, or if it's real impedances, it's just source resistance matching. So if we take that, the result here, VRMS squared over 4R, let's say part A, and put that into our VRMS squared as 4KTRB, what happens is we have this here, so we get this for the available power. It ends up being independent of the resistance, and the 4 goes away. So sometimes people refer to this as KTB noise, Boltzmann constant, temperature, and the bandwidth. That might seem interesting to you that it can be independent, but with maximum power transfer, that's what's happening. So here's a fundamental example. I say fundamental because it's something that I end up using if I have to do this sort of modeling. I'm going to assume room temperature to be 290 Kelvin, and let's just find out, independent of bandwidth, what the available noise power density is at 290 Kelvin. And from the KTB up here, I just take KT, plug that in, and I get 4.002 times 10 to the minus 21 watts per hertz. So in a comm system, we generally work with signals in decibel watts and decibel milliwatts. So 1 watt corresponds to 0 dBW, 1 milliwatt corresponds to 0 dBm, and these are just the definitions. Those of you taking the lab class dealt with this when? The very first lab, right? I got you started on this because it's just the way the instruments work. So 1 watt or 1 milliwatt. So when we plug these values in and want to get it in dBW or dBm, we get these two results. And this one right here is the one that I was told ages ago and by my professor, remember this number. I've remembered that number, minus 174 dBm per hertz is the noise level off an ideal resistor. I mean, a resistor, say, in a 50 ohm environment, the noise power at the input is going to be minus 174 dBm per hertz. Sound okay? Like, why that number? It's the physics, right? It's not something that you can change it if you change the temperature. That's really the only thing we have available to us. We can change T, we can't change Boltzmann's constant. So it turns out, though, that there's more, there is a frequency dependence on this thermal noise power in the maximum power transfer idea, and that would be due to the physics again. So we get Planck's constant involved, and so we have a roll-off of the noise spectrum, but it occurs, it's flat to very, very high frequencies. Infrared is right in here. Millimeter waves that we use, like 30, 40 gigahertz, are down in here. So it's still very, very flat unless you're at a very cold temperature. We do have quantum noise, which is this overlay on here, which is rising up. But again, in terms of interfering with most microwave communications, it's just this 290 degrees Kelvin, which is the minus 174 dBm per hertz. If you ever get involved with this and somebody says you didn't take into account this or this, maybe you'll have to remember, oh, there might be more involved, or you're going to be working in some system that does have, this does factor in. Okay, so now we're officially done with that. The biggest takeaway from that last little discussion with maximum power transfer is just minus 174 dBm per hertz. So now we're going to talk about RF subsystems, bringing the signal from the antenna through some feed lines, maybe some filters and amplifiers, mixers, and so on. How do we characterize noise performance? So we do that usually as a cascade of subsystems, because you don't have just one element in there. You're going to have filters, mixers, transmission lines, and connectors and other such things. We'll eventually be modeling what the antenna imparts to. The antenna will bring in a noise temperature associated with the antenna and where it's looking at in space. But just thinking now in terms of on the lab bench in front of you, you've got a source from a generator, let's say, R0, and we have a signal to noise ratio at that point, and then we have a subsystem 1, subsystem 2, subsystem N, and why these SNRs are shown, I shouldn't wander because it's going to be echoey at this point. What do you think is going to happen as you move down from one subsystem to the next? Is it going to get better or is it going to get worse? What's your intuition? It's going to get worse. Why is that? Each subsystem will contribute some noise of its own, right? It'll have active circuitry in it and other resistors and things. So we have a cascade. So we characterize a system, a cascade of subsystems, or just a single subsystem. Just take the L subsystem. What is the noise figure? So the noise figure is the amount that the signal to noise ratio drops as a result of going through this subsystem. So we have some temperature and we have some attribute of the subsystem that says that the S over N at the input is now going to get degraded by 1 over the noise figure. And ideally, if the noise figure is 1, there's no degradation, but the fact of the matter is there's no system except something at absolute 0 that's going to be 1. It's always going to be greater than 1. It may be very, very small, though, and generally noise figure is given in terms of dB, so it's important to note that in the calculations that go on in this section and in the homework and exam stuff, it'll be F in dB will be 10 log base 10 of the noise figure as a number. Most of the time what this is going to amount to, you'll be given a component that has some noise figure, and in the calculation you're going to have to get back to FL. So you're going to do that by taking 10 to the F in dB over 10. You're just going to do an anti-log. Does that make sense? That in this whole appendix, this is the types of calculations will involve going from dB to ratios and back and forth in different ways. So that's really the most common way of making a mistake, getting twisted up. So if the noise available signal power at the input is the voltage squared over 4 times R, and that's our maximum power transfer formula again, then we can come along, and here we're talking about the available signal power, so now we're going to talk about the available noise power that goes along with it is going to be KTS times B, where TS is the source temperature. So we have some relationship for the signal power. The signal power just gets the gain of our device in the cascade times the input signal power to the output signal power. What happens to the noise, though? The noise gets the noise figure built up into that. So we've got, this represents the noise power at the input, and this is the noise figure of the system. So overall, what comes out of this is the 1 over FL. But from that, we can imply what is the relationship for the noise figure. It's going to be noise power at the output divided by noise power at the input times GA, the gain of the device under test. So we can break it apart into two pieces and say it's going to be the noise figure, or the internal noise, plus the noise at the input times the gain, and that will be the noise available. So that's the other equation that you can write out to say what is this PAN. So then we get this nice equation here, which tells us how the noise figure is related to the gain and the internal noise, and we can basically come up with a standard equation, which is this one right here that just says noise figure is for a component generally specified in terms of 290 degrees Kelvin, and then that's how the manufacturer gives you that value. Now, when I was in school, or I was reading specs and requirements, what would happen if the customer said the noise figure was a really tiny value, but it had to operate at a really, really cold temperature? That would be kind of, not telling you the whole story. Most everybody's going to want to use it at room temperature, so they could make the component look better than it would in practice by rating it at some really cold temperature. Measurement of noise figure, I think I'm just going to not go through that, but there's a couple different methods that are talked about here in the notes and in the book. My experience with working at companies, I was involved with creating a low noise preamp for an optical comm link, and when I got done, I had to see if the noise figure met the requirements for the component, and I had a noise figure test set that I used to get the measurement of the noise figure. So that's generally what companies will have. They will have some test set, like Keysight makes them, other vendors do, Rohde Schwarz, etc., for measuring the noise figure of some component. Generally, you spec components based on noise figure and you buy them that way, but sometimes in the lab you have to verify that the component's doing what you paid for. So now I'll move into another way of characterizing a system. We can use the math that we've been going through, and we can come up with the equivalent noise temperature when we have something that has a non-unity noise figure. In other words, it will be hotter in an electronic sense than 290 degrees Kelvin. And I'm just pointing that out in this fashion because if a source is at like 400 degrees Kelvin, does that mean it's 400 degrees to touch? You're going to burn yourself on it? No, it just means that there's a bunch of excess noise associated with that device, and it looks as if it's hotter in a noise temperature sense. This section of the notes is not probably my favorite section to just go through it and say how we can play around with noise temperatures, but this equation over here is what we're going to come back and use. So I'm just going to move on to effective noise temperature. Effective noise temperature ends up being, this is the most important takeaway right here, is that noise figure and effective noise temperature are related by this. So if somebody gives you a noise figure, you can calculate what the noise temperature is, or if you're given the noise temperature, you can calculate the noise figure. So this is what gets used in a lot of the problems, just using the red outline that I gave there to say that's how I can go back and forth. If they give it to me as temperature, I can get noise figure. If I need it as temperature, I can get noise. I can go from noise figure back again. And this brings up the point of whenever you're doing something like this, you go back to the original calculation of KTB noise, and we have units of temperature if we normalize accordingly. So I think, I don't know. I was taught at my young age for learning this was when I was taking freshman chemistry. Always work with your units, right? Make sure they make sense. Have you lived by that your whole engineering career so far? Check units, so on. So if we combine this equation and then what we had before, how the noise figure, the internal noise and the noise driving it comes to produce the noise at the output, we can combine them together and we have TS, the temperature of the source, and TE come together in this equation to produce the noise power. And this is used in certain types of calculations. So that's a given thing. I'm highlighting certain things because you're going to want to create a crib sheet, right? Even though you might have the book, we talked about that before class started, and I'm going to reiterate that when we do the review for the exam. But you should still make a crib sheet that has the key things, all the things that you really use when you work the homework problems. So these are the types of relationships that matter. Okay, so now we're going to get to sort of the end of the line here. What is the cascade of subsystems in terms of noise figures and noise temperatures? We start off by saying we have a source at some temperature TS. That's this TS over here. What's going to be the noise at the output? Well, we're going to be using this equation right here to get it. GA is going to be the gain all the way through the system, but we're going to do it as a cascade. We're not going to do it, we have to do it as a cascade formula. So when we have, say, two elements like this, when we want to get the noise power at the output, we know that the signal is just, the amplified noise, from the input is just going to be this. So that's like step one. And then the internal noise from amplifier one comes through the output, but it's referenced always at the gain of that device producing it, and then it goes through the second stage and just picks up the gain. So here we have the particulars of that's what stage one is putting in for a noise temperature, the added noise, and then finally the last stage adds in noise as well. So when we write that out, we get a formula that looks like this. We're just doing our algebra. So we're going up to this equation, but now I'm going to expand it out because we're trying to look at the individual individual blocks in the cascade. So this is a cascade, and this is the noise power at the output from the input. Everything's in here, though. TS, you're given that. That's the source. TE1 is what? In this formula, it's given as temperature, but if you were given noise figure for the device, you'd convert it to temperature, and then you can use it that way. Or you can use noise figure directly if you use a different formulation. I'm going to show you that in a second here too. But this is like the starting point for getting the noise power at the output of a cascade. So this is, and this can be generalized by just adding in, more plus signs, more elements in the cascade. When we get done, though, we can see that the noise temperature, effective noise temperature of the cascade is this. It's TE1 plus TE2 divided by GA1. So that's really important. And it says since F, that's the red boxed equation up above, written down here again, is related this way, we can rewrite this and say that the noise figure of the cascade is equivalent to F1 plus F2 minus 1 over GA1. Now, this needs a little bit of explaining because there's no dB units in here. So this is known as Freeze formula. Dr. Song would usually lecture on it in EMAG 2. And you're witnessing it, right? You've seen it before. So we can get noise figure from this formula, or we can get noise temperature from this formula. We can go from one to the other. It's going to be your choice how you want to do it. But I'm going to try to write with my pen right now, if it will work. Everything in those equations, whether you use F or equivalent temperature, they're, or effective temperature, they're all ratios. So usually you're given, now my pen's not going to work for me, in dB. You're given temperature in Kelvin, of course, but so the lower equation will work directly, but the gain units have to be as ratios too. So if it was 10 dB, that's a factor of 10. If it was 20 dB, that's a ratio of 100, right? Is everybody following me? Working in dB is the best way to go for the link budgets, but in this calculation, you have to work with ratios. And this is just an example. It just says that if you have an attenuator in the line, that's going to take the power, reduce it by the attenuation value L, and this would be a ratio too. If it was a 10 dB attenuator, it would be a ratio of 10, but if it was a 20 dB attenuator, it would be 100 and so on. But going through this it's a good little example to just show how we can go through the equations we already worked through. We're trying to find the noise temperature and noise figure of an attenuator, and I'm just sort of sliding over this because I'm running out of the time I want to spend on it. But we can go through and show fundamentally that the result is in the blue box here. The attenuator has a noise figure equal to its attenuation value L, again, a ratio. But if it was a 10 dB attenuator, it would be a 10 dB noise figure, because 10 log base 10 of both sides of that equation would get you in dB units, right? So what this is telling you is that attenuator is bad, bad, bad for your receiver. It drops the signal down into the noise fast because it's attenuating it to the noise floor. So a 6 dB attenuator gives you a noise figure of 6 dB. And this is a little example that's in the book, and I put in the notes. It just says, suppose you have an attenuator right up front. Did you put that there? No. Did the feed line do it? No, so you have loss in your cable. And that's what we're talking about here, feed line loss. So when I say, did you put it there? You didn't want to put it there, but it ended up being there because there is some loss. So even 1 dB of attenuation in a feed line is a 1 dB noise figure hit right at the start of your receiver. So it does matter. And what this example sort of goes off into, it's an example of the type of problem you have to work in the homework for the final, is that in receivers for weak signals in most SATCOM systems, you put an amplifier right at the antenna. You have the amplifier right at the antenna, it drives the feed line, and then it overcomes the attenuation of the feed line because of the mathematics that we just were looking at over here. Take either one of these, but if you have a low noise amplifier right here, and this was an attenuator, this would be like, if it was 6 dB, it would be 1.414 for its noise figure minus 1, which is a pretty bad hit. But if the gain associated with your preamp, which has F1 for its noise figure, then this term gets minimized. If you do it the other way around, you take a bigger penalty. And the only person in our class that does radio as a hobby is Kurt. So do you have a preamp on your receiver at the antenna, or just take the loss?
Yeah, there's a there's an attenuator too. Sometimes if you turn that on, it'll pick up a ton of noise from the transmission line.
Mm-hmm. That's probably that's an interference thing, but most amateur radios people, at least my father, never had an amplifier, a preamp on his receiver, because it also requires a diplexer then.
I think there's one built into the radio. I don't have a separate unit for it.
Okay. The diplexer idea just is the idea that you might receive on one channel and transmit on another, but you have to separate the transmitter signal from the receiver signal, so you have something called a diplexing filter that will separate them. So we go through this example, and this just shows you an approach for how you're going to use Free's equation. So here we're given everything in dB units, gains and noise figures. So I convert from dB back to ratios, and this is what I'll be looking for in your exam when you have a question like this, that you faithfully track this all the way through. So the attenuator is just the 1.414 in this case because it's feed line loss of 1.5 dB. But just track this all the way through, and now you can use the noise figure equation, which was the upper one, or you could switch to noise temperature if you wanted to. So when I did the upper one, I get 7.19 for noise figure, and then in dB, which is 10 log base 10 of it, I get 8.57. If I want to get the effective noise temperature, I can convert it right here directly using the same equation that I referred to earlier, 1796.3 degrees Kelvin. And remember, this is not physically hot to the touch. I mean, it's just figuratively speaking what the effect of the noisiness of the receiver is. It looks very hot, and hot is not good, you know. So how can we improve the performance? What you could do in this case, put an RF preamp in front of the cable right at the antenna, and then with this example, we're going to take this RF amplifier, we're going to call this our preamp, we're going to move it in front right at the antenna. So in the cascade expression, the numbers are just reworked here, and that drops the noise temperature or the noise figure down to 5.15. So it's in dB, it's 7.12 and 8.57. It's not huge. The way we could minimize that, though, would be to have a higher gain in the preamp. This is only 20 dB. Maybe you'd go with 30 dB or something like that. What's a disadvantage, though, of having a lot of gain right at the antenna is that it can overload very, very easily. So it's just, you got to work the system with filters and how you set up your RF components in the system. So that kind of ends this section. The only thing this next example does is it says, now suppose we have a source or an antenna that's at 400 degrees Kelvin. So now we can take this example, the first example, which got us noise temperature and noise figure, and what we're going to be doing is we're going to be working this equation right here. We're going to get the noise power at the output, including the noise temperature of the source and our equivalent noise temperature from the cascade model. So this would be so you'd get that as your effective noise temperature for your cascade. And if I haven't really said this, and you don't need to worry about it for your work, for this class, but what most people I've worked with do is they put all these numbers into a spreadsheet, and they just use like an Excel spreadsheet, keep all this RF information in there, and that way they can move things around very quickly and look at different ways of doing things. So driving down to continue this example with the feed line and now having a noise temperature, now we calculate the available noise power coming out over here. I can't do that. We're kind of heading in the direction of is at the end of the receiver where it goes to a demodulator or detector or something, what is the noise power output, and then what is the signal power output. So right now we're focusing on the noise power. So we'll suppose that we have a system bandwidth of 100 kilohertz. We're at 400 degrees Kelvin. What's the maximum available noise power? So we're going to use this equation right here that was up the page and I highlighted. But if you want to work in dB, it's easier or more convenient to play some games. So we have KT0 that we bring out in front, and we have GA, which we bring out in front. This is the gain of the cascade. And then we put these numbers all in one term called TS plus TE over T0. So this is a normalized noise temperature of the cascade with the input, and then the bandwidth B is set out in front too. So what we're doing, and this is going to be your preference. I say your preference, meaning what do you like more? Do you like multiplying or do you like adding? And when working in dB, adding is kind of what you do. So you say, okay, what is the gain in dB? All of these numbers are multiplicative, so they're all going to be dB values that we add here. GA is just all the gains throughout the cascade, and then the KT0 is going to go back and use KT0 minus 174 dBm per hertz, and then we multiply times or add 10 log base 10 of this ratio. That's this, and then we add 10 log base 10 of the bandwidth. And this becomes a better way, in my opinion, of working numbers. I will love it when you work problems like this because I'll be able to follow it with just addition and subtraction. But you got to stay consistent. You can't mix multiplying and with logs. You have to be in the log environment or in the ratio environment. So in this case, the number works out to be minus 28.71 dBm. And how do I know it's got units of dBm? This is dBm per hertz from KT0, and this is per hertz. And what are the units associated with this? It's died on me for whatever reason. I don't know what happened. I don't know what went wrong. It's hertz. I started to write H and I couldn't get the crossbar and I can't put the Z at the end here. But this has got units of hertz because that's what this is. So when you work with decibels, you kind of have to imagine how the units cancel accordingly. We have a dBm per hertz associated with this guy, and then this term has the hertz, so that cancels that out. And this is dimensionless because it's just 10 log base 10, the ratio of temperatures. So, and this is got, this is a gain, which is dimensionless. It's 86.5 dB. So this carries the unit of dBm because that's the unit associated with KT0 dBm, and the per hertz is canceled by the hertz over here. So you might say in an example like this, what must the received signal power at the antenna terminals be for a system output SNR of 20 dB? So what we'd like to be able to do is be 20 dB above this for our signal power. So we're going up here and we're saying we want to make this sit 20 dB above the noise power at that point. So we just go back to look at it and said, well, what is the received noise power, or what is the received signal power at the output of the cascade? It's going to be the input signal power divided by, or multiplied times the gain, and then we want that divided by the noise power to give us a dB value of 20. So we just, again, tear this apart. What's going on here? Why is this not working? Okay, I'm remembering the last time this happened, it was the 2.0 died. I have to restart it again. And I'm about ready to take breaks, so I'm not going to do it. I'm just going to say, though, we have GA times PS. So if we want to work in dB, it's just going to be the gain in dB plus the gain, or the signal power in, or signal power over here that we're trying to solve for. And then we have this in the denominator, so we have 20 minus or plus the noise power, because that moves over there. This is so awkward when the tool dies. Do I need to explain more about this? I can't draw on it right now. Drawboard is good a lot of the times, but then it fails on me. I've used other PDF editors. They fail on me too. At any rate, I'm just trying to pick this apart and say, now this should work again. So move all those to dB values. And this is already a dB value. So if I want to solve for PS in dB, I can just put that on the left-hand side, and then I'm going to subtract the gain in dB on the right-hand side. I'm going to add the power in dB on the right-hand side because this was in the denominator. So I just get this nice expression which tells me I need to receive minus 95.21 dBm at the receive antenna terminals. Now am I messing you up because you don't like dB or have never had to use it before? It's just, it works out a lot nicer. So you just have to think in terms of 10 log base 10. Ask me a question, and if you're okay with it, you're just going to have to practice on the homework. If you don't like this idea and want to work with just the ratios, do all those conversions. But if you want to learn to be more confident in it, just work it both ways until you get confident that it works for you. So the last frosting on the cake idea is this got us to the point of saying, we want to receive. We know now what power we want to receive at the antenna terminals to get 20 dB signal to noise ratio, and then that will relate to what we looked at the end of chapter 4, the pre-detection SNR. What do we need to get error probability, output SNRs, and so on and so forth for a particular noise level. which is controlled by the noise figure and noise temperatures of the elements in the system. The next thing is to now put an antenna on the system and look at the physics of the antenna. So free space propagation is what this last little bit is. And this is kind of like I said, the frosting on the cake. We have a ground station, we have a receiver, we have a satellite relay. So in SATCOM or any type of comm, you always have a link budget. And the link budget brings together these things we've been talking about in this appendix. And that's why we go through the appendix, because a link budget is always there in a comm system. You will bump into it, maybe not immediately, but somebody will say, well, is this going to work? Is our link going to work? So you'll need to be able to have this sort of modeling available. So by adding in the antenna, we add in another set of attributes. We add in an antenna that has some gain. The basic, simplest antenna is the isotropic radiator, which is the ideal omnidirectional antenna. The way I think of it from electromagnetics, I think of it as a point source. It's just a dot sitting there, and it radiates equally in all directions. It radiates and it receives both energy from all directions. But in terms of the transmitter, I'm now thinking of it as a point source. So what does a point source do? It creates what type of a wavefront? Think back to physics. Is it a spherical wavefront? Is it a conical wavefront? It's spherical, right? It's just radiating a spherical wave in all directions. So the key in this basic antenna modeling is we get a distance d from the point source, and we have power density, because what's the power that's driving the antenna element is so many watts, and it's painting it on the inside of a sphere of radius d, and it's going to paint so many watts per what? Meter squared, right? Because it's the flux density, watts per meter squared at some distance d, or flux density. So the power density at a distance d is transmit power PT divided by 4 pi d squared. And that formula is like, I've seen that before, right? That's the surface area of a sphere. So watts per meter squared. This would be more of Dr. Song's type of teaching from the antennas class, but comm systems engineers can do modeling like this. Every discipline has got crossovers, and here's where we cross. So then we use antennas that aren't point sources on satellite radios in particular. Cellular antennas generally are not an omnidirectional, but they're more omnidirectional-like. But in a satellite antenna, it generally has directivity, which means power radiated in a particular direction. So you have a power gain associated with the antenna of GT, G transmit, over the isotropic antenna. The isotropic antenna radiates equally in all directions. An antenna with directivity radiates more power in some directions and less in another. I think if you wanted to draw a really simple picture of an antenna, and I didn't want to do that again. This is how I get into trouble, though. This is kind of weird looking, but thinking if you're looking at the antenna the top down around all directions, it has a certain amount of gain, really small, and then in some directions it's very large, right? Taking it in the limit, it has no gain in anything but the beam width of the antenna. But this aperture antenna is typically is the type of antenna that represents a parabolic dish. So it has an aperture area AT, and as long as aperture area, effective aperture area, is much greater than lambda squared, the wavelength of the RF signal, then the gain of the aperture antenna is 4 pi AT over lambda squared. This is just a result that I'm just giving to you. 4 pi AT over lambda squared. And the aperture area is, again, the concept from over here that represents an area out in space, distance away from the antenna, that corresponds to where it's radiating all its power through that aperture area. We assume that the receiver also has an aperture type antenna with an area AR for received, then the two antennas are pointing to each other. One puts out flux density in that aperture area of so many watts per meter squared. The other one collects it with a certain aperture area. So the aperture areas combine together to form received power. So you have a received power, it's collecting so many watts per meter squared from the transmitter, and so you end up, when you combine the two, you get gain of the transmit antenna, gain of the receive antenna. Lambda squared shows up in there because it's part of the definition, and then you get 4 pi d squared in the denominator. That's the range, so this is an important attribute. Is it somebody close by, or is it a satellite up at geostationary orbit, that radius away? So we can make substitutions and do some extra massaging of the math for P received, and you can factor out lambda squared over 4 pi d. That is the so-called free space loss. I'm willing to bet Dr. Song has mentioned this before in antennas. That is just a function only of the wavelength inverse to the frequency of the carrier and the distance between the transmitter and receiver. And then you have the other attributes, transmitted power, gain of the transmit antenna, gain of the receive antenna, and then this factor is just a fudge factor. It's saying we don't want to have loss, but we know we're going to have some loss in our aperture antennas. What's an idea in your mind about why an antenna would not have perfect, would be loss-free? Just think physics. You build a parabolic dish, and it's supposed to focus in one direction, but you're going to have imperfections in the surface, right? It's going to not be perfectly smooth parabola. So, and then the materials and other things. So that's where the LO comes in. Something to represent some physical approximation to loss. So putting that together now, the P received in dB is 10 log base 10. The P received is a ratio. And now start plugging in the rest of the terms for PR. And that's coming from this equation up here. So we're going to have how many terms? We have 1, 2, 3, 4, 5 terms if we want to think of it in terms of working in dB. So we have the 2 here gives us a 20 log base 10. So that's your free space loss in your channel model. The next term is the transmit power in dB, the gain of the transmit antenna in dB. So that's called effective isotropic radiated power, another term from electromagnetics, but all transmitters have EIRP. And then we have the gain of the receive antenna, and then in the denominator, so we have the minus sign, the antenna loss fudge factor. So that's going to be our received power in dB due to the signal. So if we put all this together, we're trying to come up with an equation that tells us whether or not we meet or exceed the expectations to get a valid link. And a valid link means the signal to noise ratio at the receiver is greater than some number. So these are the parameters in this simple model. It's a geostationary satellite, bandwidth 2 kilohertz. That parenthesis is not supposed to be there. 3 dB loss in the antennas, Receive antenna gain is omni, so it's 0 dB. Maybe this is what I have in my car with my patch antenna on the roof for Sirius XM radio. There's more to it than that, but and then receive noise temperature, which would be computed under the hood using Free's equation for TE and TS for the source, 1000 degrees Kelvin, and then plug all this stuff in and use the fact that the carrier frequency was 400 megahertz. Yeah, 400 megahertz in this example. Speed of light, and then you can finally work it all down to get the received signal power minus 111.74 dBm, and then back out of that, calculate the noise power based on the attributes for noise temperature and temperature of the source, minus 135.62 dBm. Bring these two values together, and our SNR, post-detection SNR, is 23.88 dB. So if this link needed to get 20 dB, it would be there. If we needed to have extra amounts in there because of rain, fades, and things like that, maybe that's not good enough. But remember we talked about rain fading earlier and other phenomena that occur in propagation. This is really, though, the culmination of pulling all the stuff together all the way down through Appendix A. No calculus, right? We're using models of antennas to simplify things, but this is the way a systems engineer would do stuff. And like I said, most systems engineers would store all this information in a spreadsheet. But when I was working at Augustus Aerospace, for the CubeSats that they were making for their customer, which was the Army, all this stuff was in a spreadsheet, and the customer knew it. And then they would talk about, getting different things to work properly and how that impacts the original link budget design and what was going to happen in the performance. I took over from my current boss, who left the company, but I now work with again. I took over his spreadsheets when I was talking to things through with the customer, so I inherited his spreadsheet. But what's one thing nice about spreadsheets? They're generally pretty easy to catch on to, that you can pass them around and you can get that information, and then you can make changes and trade-offs and things. It's a nice tool. Python is overkill for a lot of the stuff, and the spreadsheet is just so easy to move from one person to another. So these show up in the homework problems. I want to take a 10-minute break just because I don't want to run out of time. If we can do that, and then we'll come back. Oops. And my earbuds did not work today. It was causing crashes at the beginning. So we're recording, and it'll be more of an echoey sound, but it is what it is. So I've just got finished talking about this. So what I've got here, let's just go through what we talked about when we were offline, so that information is captured. So the final exam is going to look just like the exam you took 2 weeks ago. It'll be 5 pages long. It will have the same number of problems on it. It has to fit into a 2-hour interval. It's the exact same idea. And as I pointed out in the beginning of class when we were looking at frequency division multiplexing, the problems and actually other problems are on those old 2 finals. Two old exam 2s. So those are resources for more example problems. There are no old finals because they're what they are. I just don't put them up there. But you have the information that's in this document. So, you have that to go through, and we're going to walk through that. I'm going to try to write on it, and then I'll repost this. This one I managed to change the date on it when I got home because I couldn't push it out there yesterday from Switzerland. But it was written for 2020. So I'll make notes on this, and since I told you yesterday when I was in the airport, I said you might want to bring this in. Did anybody bring it in, or you can write on your tablet? Okay. So notice right now that there's an extra page at the back. So if you want to reference stuff, you can write notes on it further back. But I will push up the original blank one, and then I'll push out this one with the notes that I write on it on the website. So we've already talked about the format of the exam, the 5 pages. What we didn't talk about in the video in detail yet is the fact that we have come to terms with the people that are in class today that we have a paper copy of the textbook. So we will have open book, and do we have confirmation that somebody's going to make copies of the note chapters so that we can have in class? I mean, I suggest sharing the cost. I don't have it. And I can't run it right now. I'd have to spend time. I'd rather go home and sleep at this point. But I'd like to I want open notes as well as open book. And it'll be shared at the front of class. So any of you that are watching this video, if you have a paper copy of the book, please bring it in. We have 1 copy committed at this point, and you will share it. And hopefully we'll have 1 copy of the notes. I will investigate whether or not I can run those, but I'd rather someone of you agree to make them. And you can put them up 4 to a page, or there's things you can do. Last semester when I taught DSP, somebody had them and they brought them in and they shared them. So maybe, again, someone of you that watches the video has that because you've made that copy yourself. Let me know on Slack so that I know that we will have it. If not, you won't have my notes, but you'll at least have the book. So then you will be able to have the same crib sheets you've had in the past. You can write a crib sheet for the final 1 2-sided page, 1 2-sided page from exam 2, 1 2-sided page from exam 1. Will make your portfolio of study material. You can have your calculator. Now, a related matter that I talked about early this morning was that one person had an emergency 2 weeks ago and was not able to take the exam. That person still wants to be in the class as far as I know. I think now I'm hearing he wants to take an incomplete. But I would like to give him the opportunity to take the same exam that you did, and I'm hopefully going to be negotiating that very, very soon. So I'm not going to be posting the solutions to the exam. So what my alternative is, depending upon when and if he can take the exam before next week, I will push the exam, which Charant had in his possession already when he gave the exam, out to you on Slack, direct message channel. Reasonable? I don't know what the score is. You guys can tell me how did it go. I will see Charant right after this, but I haven't gotten any feedback because I wasn't really receptive when I was traveling. But am I going to have an easy time, or is it going to be hard?
Easy time grading?
Yeah.
You're probably going to have a hard time grading, honestly.
Okay. I'm not looking forward to any of this. I'll just tell you one thing about being a professor. Grading sucks badly. It all depends upon things, and I can't control it either, but it can be very time-consuming and not very time-consuming. But needless to say, I still have my standards, so I'm going to do the same thing that I've always done. I'm definitely not going to get exotic with things. So let's just talk about that at this point. So what we already talked about earlier in class was this exam from 2019 was helpful for the homework. So if you came into class late, you want to watch the early part of the video and see the discussion on one of the homework problems there on frequency division multiplexing. You might want to watch the video that I sat at home and created before I left. It goes through stuff also in Project 2, not now it's coming to mind, I needed to mention Project 2 because one team turned it in, right? You turned in your Project 2. I didn't feed back to you, even though I looked at it. It looked like you got the right stuff. You got it all to work, right? The main thing is it'd be in a Jupyter notebook, printed out as PDF, so I can just read along, and it's just like what's in your Jupyter notebook. And I've showed you that in class before. You just take your Jupyter notebook, export it as HTML, works the best for me, and then use a browser like Chrome or Microsoft's browser, and it converts it to PDF pretty nicely, and that's what I want you to give me. If you want to have the figures that I had in the document originally, you have to make sure to have those figures in whatever folder your HTML document is. What I'd recommend is export to HTML, put that HTML file back in the same folder where your Jupyter Notebook is, and that way when you render it into the browser, it will say, oh, the figures are right there. We'll find them, and then when you PDF it, they'll be there. And you can put in the page breaks and things like I've talked about before, and that's pretty much good to go. So one team turned it in, they got the right kind of stuff happening. I pretty much give you everything, but you have to play with it, and that's the whole idea. You got to learn how to play with it and make it work. I'll save time for that, and if we don't have time, I'll carry on a discussion on that in the lab right after this. Are you guys taking an exam today?
I sure hope not.
Okay. I asked him again from the airport yesterday, let me know. I haven't heard from him, so he's probably going to have you do it next week then. At any rate, now we can go back over to this, get inspired. So this walks through each chapter. Chapter 2, what I've got X'd out are the sections that we did not cover from exam 1, so it's the same. It's the notes pages, the same. And even though I'm fatigued and weary right now, I'm going to be looking at this to make sure how I put the exam together follows this rubric. This is kind of like the rubric or the roadmap for chapters 2, 3, and 4 in Appendix A. Chapter 5, we didn't really use it. I reviewed it on the plan yesterday just in case I had the time to talk about it. But an introduction to digital comm that you've gotten from the write-up for Project 2 is sufficient for any question I might ask, which would be a short answer question. It's not going to be a work out the numbers type problem. It's just going to be digital modulation. And probably the most important thing in digital modulation that you get introduced to in the project is exactly what we were talking about at the beginning of class, the quadrature multiplexing idea, the fact that digital modulation relies heavily, the most popular schemes rely on this, and that's exactly what you're playing with in the project. QAM is quadrature multiplexing, is what it's doing, except digital is for M1 and M2, but exact same idea. So don't worry that much about chapter 5. It's there. You can look at it if you want to, but you've got an introduction to that, and it would be at most one problem. So, okay, then what I continue to wheel on through here is specific topics. So this is like my review for the exam, and the exam is going to emphasize new material, and that's where I have to make some changes in what I've got written down here because we've covered things differently than what's in this sheet, and I will try to clear that up when I repost this again. So signal models, it's behind everything that we do, but drilling into the core crazy details is not, not a theme for the final. I've only got 5 pages, so signal classification, you just use it. I mean, you've been using it, right? Inherently, you just use it. Hopefully you feel like I know something because you just know how to think, right? it's an energy signal or it's a power signal, and this stuff makes sense. Fourier series, the idea there was to just understand harmonics and spectral content, and then that merged with Fourier transforms. I think you should be good at that too. So it's just the stuff that makes sense for comm systems. For example, trig identities could show up, not necessarily in a hard work fashion, but it definitely could show up. So, but you've been practicing at that, so it's fresh enough in your head, right? Unless you went out on a vacation like I did and wiped your brain, and you have to reload it all. And I don't have to reload it all because I have my crib sheet, right? Power spectral density, we like to use that all the time. I think I had a question on that on exam 1, and if there's anything that I would do specifically in power spectral density, it might be to look at something that was not done well enough that I might want to just retest on something. I don't have anything in my mind right now, but it's autocorrelation function in power spectrum. And the power spectrum is probably the more important part because we're drawing pictures of spectra all the time, and that's just kind of the norm for comm systems. LTI systems, of course, is the backbone of everything, so you have to understand the fundamentals of LTI systems, because even in drawing the block diagram, like I talked about for the FDM systems, you want to have the behavior level modeling idea of a low-pass and bandpass filter. You know that the filter will have, ideally, it will have zero insertion loss, will have no group delay, but if a filter has some group delay, then like in Project 1, we compensated for it by putting, say, in the Hilbert filter, remember, we put a delay in there to compensate. And I don't know, I haven't really looked at the projects much. I did work out one solution. I worked out the details to Project 1 when I had some time in Typest, because I could do that on my tablet. So that system is actually pretty good, Typest, which I don't think anybody has used that much in this class, but I could do that remotely. Was that project fun in the sense that it worked? I think there's some pretty cool stuff you can just learn from that whole exercise. So, and that's where LTI systems is at play, definitely. And sampling theory and the Hilbert transform, that can show up in a subtle way, like if I wanted to retest on the problem that involved time division multiplexing that you did do on the exam, and I haven't graded yet, so I didn't know how it came out, but there was a little bit of thinking required on sampling theory, right? You had to take an analog stream, and you had to sample at a greater than twice the highest frequency, and things of that sort. So maybe close that door. So the main crux of the matter is chapter 3 and 4 with the add-ons that we've done since exam 2. So linear modulation shows up at the high level from things that we were even looking at today with FDM. Short answer question could be, I could ask, one disadvantage, one advantage of anything that's in the list for linear and analog. So that could be a short answer. But in terms of being able to work with it, block diagrams, double sideband, it's the crux of digital modulation too, but it requires the coherent carrier recovery. So it's what we have to do when we want to do well. Amplitude modulation is what you can do with less investment, especially when it's an asymmetrical kind of a link. And we've talked about that a lot. A lot of people listen, you want to make the lower cost receiver. If only a few people transmit, you put more money into the transmitter. Single sideband, I'm not super excited about it in the sense of where it has come from, but in the example of Project 2, I think you got to see where a Hilbert transforming filter has got some neat properties to it. Vestigial, no problem. And I say here, efficiency, it would be kind of poor of me not to at least see if you understand the basics of AM and what I say here, expect a problem. This one, I can't answer this question. I'll just say perhaps is about all I can say, because I did have you do some things on the exam, but I haven't seen it yet. Hopefully we'll have it back in my hands today. You can tell me what you think, though. You had to draw an instantaneous phase and frequency. I may not remember exactly what the problem was, but I still could come back and revisit that. Carson's rule. There will be something where you get to think about Carson's rule. Even the example I did early in class today with the frequency division multiplexing, Carson's rule showed up in there. So expect that to definitely happen somehow, somewhere. So there will be, it'll touch upon it somewhere, somehow. Narrowband to wideband conversion, you saw that in homework. I don't really intend to revisit that. Something with demodulation of angle modulated signals definitely shows up. I mean, I think I mentioned earlier today was that demodulation of angle modulated signals involves, from our experience, either a standard discriminator in the theoretical sense, or a DSP-based discriminator, or a phase-locked loop, some sort of phase-locked loop demodulator. Those are the main go-to points. So if I asked you what are two good ways of demodulating FM, you should come to mind with a discriminator and a phase-locked loop, right? This interference discussion, about the most I can do is you can say that good things to say, and they're summarized in the chapters, is linear modulation can tolerate interference if it's not too powerful, and it does it in sort of a graceful fashion, and even with noise. Angle modulation can handle it too, but it's more subject to the thresholding phenomena, which we talked about early in class. It'll go to pieces and be gone. I mean, only 3 of you were here when I first went through this, but it's this last little topic in here. And I guess since I'm mentioning that, something about this picture could come along too, and just say, what would you do if you had to end up with a certain detection SNR, either to get low error probability or high fidelity? Which one of these would you choose? We talked about this earlier, but double sideband just linearly goes up and down. The non-coherent or the nonlinear schemes like FM, PM, and PCM digital get really good performance, but you have to expand the bandwidth and you have to be above threshold. Sampling theory. It's sort of the backbone of anything involving PCM or any digital modulation of analog waveforms. Honestly speaking, where it's going to show up is on an FDM problem, just like the homework problem, the one we went through earlier. It's just going to be needed to understand a little bit about how that system might go together, where you have either FDM or you have TDM, time division multiplexing, which you did a problem on in exam 2. Bandpass sampling, possible. You'll just have to write the equations down or put those on your cheat sheet, how that works out. You certainly, I made it pretty abundantly clear, though, that you can leverage the power of sampling theory on an RF signal by undersampling. And That's pretty valuable. No problem on any of the analog pulse schemes, amplitude, pulse width, pulse position. I consider that to be more of a control system kind of a thing. PCM, though, we did talk about, and you worked a project on it. You already had a problem in Chapter 2 on that, though. I mean, in Exam 2. I don't know what I would do with it. I don't think I really made a commitment here. Definitely no delta modulation, but PCM, you got acquainted with it, so could be a PCM-related problem. Now we get into what's new. Multiplexing is in set number 10. We talked about that this morning already, so definitely new for the final. Quadrature multiplexing is talked about today, talked about in the short video I made before I left. That is possible. I could even ask you a discussion question if I really felt inclined to want to grade that. How is quadrature multiplexing and digital modulation, how are they similar? And they basically are using the idea that you can put things on the in-phase and quadrature channels. TDM shows up in all communications, and it can be TDM and FDM together if you decide to multiplex a bunch of signals into one stream and then send that into one subcarrier and so on. But I probably will just stay more basic. I don't want to create more havoc for my grading either. What's on set number 10 and what's in that old problem we looked at the beginning of class today is the type of thing that I'll probably go with, something like that. And those, the three of you that were here from the very beginning, that seemed pretty reasonable, I think, right? You have to draw a block diagram, but again, that's just to refresh our memories to make sure there's no doubt about that. It's this problem from this old exam, and then you have it in the homework problem. You have it as number 2 right here. So one and the same type of problem. So work this problem, and then you'll be set for doing it on the final. So general performance modulation and noise, we already talked about that. Short answer question or a curve or something. It will be a 5-pointer type problem. It won't be a lengthy calculation problem. It's just, do you have some understanding from that picture that we've talked about already today? So now we get into all the new stuff from Appendix A, which you also have practice on with set number 10, which I, now that I'm thinking of it, I do want you to abide my request for midnight on Friday because I want to be able to post the solutions. It's just fair to everybody to not let somebody be a laggard and not get something in. Just plan ahead and get to work on them. And if you have an issue, let me know. That was the rule at the very beginning, which nobody ever did. When you can't do something, let me know, and we can work something out if possible. At any rate, physical noise sources, what do I have written down here? Thermal noise, Nyquist formula, short circuits question. So really what we're doing is we're going to X out that. Thermal noise, very first part of Appendix A, pretty simple, straightforward stuff, and you have practice on that. Nyquist formula, I've used that on the final before. And then the rest of it boils down to these last couple bullets. Well, actually that's out. We talked through today, but available power, yes, that's KTB. And just think, when you think this one right here, minus 174 dBm per hertz. That's used in a calculation, and that's from this bullet, precisely. Now, overall characterization was 2 types of things, which I worked on just before the break, noise figure and noise temperature, where the data generally comes to you in the form of dB units, but you have to calculate with ratios. So make sure to do like I did in my example today, right? I first took the data, put the numbers down. Hopefully we'll see that in your sheet where you convert it to ratio. So that way when you go to calculate noise figure, or noise temperature. I see that you've done things from dB back to ratios and then back to dB again, if requested. Cascade of systems. The significance of attenuator noise temperature and how you may want to put a preamp in front of it so that you don't get hit by the noise figure of the attenuator, which is the attenuation value. Then the very last thing we did, which I wrote some more info on here to try to explain the working in dB units, the isotropic radiator and the aperture antenna, and then working through the link budget and working through this equation in dB. So I just wrote this out again in these notes differently than it's maybe written out in the chapter Appendix A notes, but it just lets you see how you can do it in dB. I'd prefer you to do it that way, but do not tangle those two things up because you will get the wrong answer every time. Just keep your brain straight. If you want to, move your brain to thinking the way comm systems people do, work with dB, which would be, this formulation down here. If you want to work with the ratios and just crank all the numbers in and then punch buttons on your calculator all at once, one big blob, then you'll get a number that way. So I prefer the second method myself. And you can get a lot more insight out about things too, because I won't necessarily take a question like this and say, do this. Instead, I might say, find that, find the transmit power in order to get a certain receive power, and you'll factor all this other stuff in so you can pull anything out of that, right? And that's just algebra. So, or the professor I had in Missouri who had a Missouri slang, he would say algebor, and I would say the bore when he said it with his accent are you telling me that algebra is boring? What do you think? As you advance, though, algebra becomes maybe more boring than calculus. So that's the way that type of problem will work, and there will be something on that. So we went through that already. Digital communications. These are some things that are in that chapter 5, which I didn't get a chance to go through, but you got introduced to the raised cosine filter, and it's things you got introduced to in Project 2. It's short answer type stuff, like what is a more efficient filter for transmission? The raised cosine filter, the square root raised cosine transmit and receive is what you do in Project 2. That gives you much more compact spectrum than the rectangular pulse shape, and that's pretty much universal in cellular and everything that we do wirelessly. Didn't really talk too much about FSK, but you did get introduced to FSK in the lab, and I don't know how that all shook out throughout the semester, but we didn't talk about FSK. I mean, that's sort of what our Bluetooth devices use is GMSK, shaped frequency shift keying. That's a COM2 kind of a topic, but that's where we're at here. So decide how you want to formulate your stuff. You're going to have access to the book. You'll have access to, hopefully, get confirmation on that. And I'd like anybody in here to tell me, I'm taking this on. I'm going to make copies and I'll do this for the team. If you can do it, let me know. You guys can talk amongst yourself. What questions do you have for me on the exam? One last thing, we start at 8 o'clock. I can't control that. So be here at 8 o'clock. I will be here at 8 o'clock. That was in my notes on the website too, but that's university's policy. So what questions do you have for me before I fade away?
Since this is the only book, are you okay with students like taking a picture of it and then having it at their desk so you can have it more accessible?
I don't want you to use your cell phone,
That's understandable.
so no.
Okay.
But you are the owner of the book, and if that's the only book that shows up, I'm going to see if I can get access to my books in my warehouse at my house, which is, under reconstruction. But there may be a copy in the library too that I could check out. You have priority, and yeah, you might leave it sitting just like that during the exam. And if somebody looks at me and says, I'd like to look in the book, I will come and grab it from you,
Okay.
and then I'll move it back over. But if you're not using it very much, I might put that table, roll it over, and put it in the center or something. I personally think, I don't know, if it was me, I use my notes more than I use the book.
Yeah.
But I use them both, honestly. I use my notes all the time where I work, just because I wrote it down and I don't want to have to recreate it. I want to use something that I'm familiar with. So that's why I look at that as being almost more valuable. I know last fall that was more valuable than the textbook was, but I got to get a handle on that. So not today. I'm not going to go make paper copies in our department office with the way I feel right now. I just don't feel very with it. Other questions on the exam? It's going to be very familiar, and it's going to be easier because Appendix A is easy. The last few things we did in Chapter 4 are easier. Agreed or not agreed? That's how I look at it. I mean, your head has to be screwed on right. You have to be thinking. You can't just wig out, so. Project 2, let's just go upstairs to do that and run out of time here. I think the other class may come in today, I don't know. But get with me on that. It should get done early. You want to share any secrets on how you got it done so early? Commitment or something you can use good?
Yeah, my senior project I had to pick one or the other. And I'm like, I gotta get this done before I can think about the senior project.
Okay,
I stayed up super late.
okay. So you worked with a partner though, right?
Yeah, it was me and Jesse.
Okay.
So I did.
You can conquer and divide, and you guys did, hopefully.
Yeah.
Okay. I've done these problems so many times before, and I've done this and that and this and that, and then I get to going back to things that are more fundamental, and I think what you had was more fundamental. The fact that air probability curves shift out, which is really cool, and I'm teaching you something really, really important with that, is they move to the right. If you ever have a curve move to the left of theory, you want to not show that to anybody until you think about it for long and hard. It's like, no, we're never going to get better than theory. Our system's going to impair. So, and I got you introduced to that idea, I think, too. And flaring and all these other things. Those are common engineering dilemmas. Okay, I was going to play with my SDR for the lab, but I'll take that up to lab. Did I ever show this in class? I don't remember. I ran this in class, didn't I? At one point? It just crashed on me, so I don't want to run it.